No? Yes? Okay, I think we... Okay, great. So some people responded yes. That's good.
Yes.
Great. Thank you. Okay, let me just... Right. So... ROC curve. Very important topic in the classification, within the classification topic. And so let's start reading and discussing. The receiver operating characteristic, that's the full name of ROC, and the curve is another common tool used with binary classifiers. It is very similar to the precision recall curve, but instead of plotting precision versus recall, the ROC curve plots the true positive rate against the false positive rate. The FPR, or the false positive rate, is the ratio of negative instances that are incorrectly classified as positive. It is equal to 1 minus the true negative rate, which is the ratio of negative instances that are correctly classified as negative. The TNR is also called specificity. Hence, the ROC curve plots sensitivity versus 1 minus specificity. To plot the ROC curve, you first use stats function to compute the TPR and FPR for various threshold values. I want to take a pause here just so everyone kind of understands the concept here. So if you have any questions, please feel free to ask right now.
One question that I have here is, what is the result in thresholds from this? Is that not something that we define?
That's something that is actually just, this is the thresholds. I think this is directly from the Sgd classifier, and under which we use SVM classifier, which calculates decision scores, and we use that as thresholds.
So the thresholds are determined sort of inside of a black box. We don't see them, but the main point is that the precision recall curve and the true positive versus false positive curves are what they call parametric curves. Each of these quantities is a function of the threshold. And so what we see when we look at these curves are, it represents all possible thresholds. And you can choose which threshold you want to adopt in order to maximize the usefulness of the score for your purposes. So, for example, if you're really bothered by false positives, you can choose a threshold that is designed to to produce few false positives. Maybe you could decide that you want 1% false positives or fewer, and then you could choose that threshold that gives that result. But then the trade-off is that when you do well with false positives, you do less well with classification. In other words, with correct classifications, or I guess you'd call that detection.
Cool. And in logistic regression, let me just bring back to the StatsQuest video, and it's probably clearer to kind of explain it from a logistic regression perspective. Like in logistic regression, this gray line is your threshold. Like, do you want to just cut it at 50%? Like if it's 60% or 0.6, then like the mice is obese. And if it's below this threshold, then it's not obese. But like it's arbitrary. You can actually move it up or down, and with each movement, you almost create You can create a confusion matrix, and you end up with a bunch of confusion matrices. And how do you pick that? How do you pick that? It's exactly with ROC curve. So basically, you are trying to map almost like every single threshold with the ROC curve. And you get different true positive rate and false positive rate. Is that clear?
Yeah, that's helpful. Thank you.
Sure. And in the SVM case, it's just a little bit more complicated with this decision score. And I wish he could just use the sigmoid, or sorry, the logistic regression.
Yeah, in this SVD case, it doesn't output probabilities like you said. It outputs scores, but there are ways to map the scores into probabilities. And I think, to me, the whole concept of thresholds makes sense if you consider them as probabilities. So it's a threshold is like a probability at which you make a dividing line between positive and negative cases. So the default is 0.5. You know, if something has a probability of greater than 0.5, then you call it a positive case, and if less, then you call it a negative case. But you're free to adjust that threshold however you want. So you could consider setting the threshold at 0.2 if you want. Everything less than 0.2 is negative, and everything greater than 0.2 is positive. And that's what you actually do to create these Roc curves. You imagine setting every threshold possible. In other words, you have a grid of thresholds, maybe every 0.1 or every 0.2 in probability. You set the threshold there. You compute the true positive rate. Excuse me. You compute the detection rate, which goes along that's called the true positive rate, and plot it. Then and you also compute the false positive rate. You plot that point. Then you adjust the threshold to the next increment in the grid. Calculate the true positive rate and false positive rate again, and you just keep doing that until you've built this Roc curve. That's how you actually make the Roc curve.
So is the range for the threshold always going to between 0 and 100?
When you have a probabilistic classifier, that is one that outputs a probability, then it's always going to be between 0 and 1. If you have one that outputs a score instead, like the SVM, like this support vector machines classifier, then you have to work with the scores instead of the probabilities.
Got it. Okay, thank you.
Cool. Okay.
Emma, can I make a comment here? So
Yep.
regarding this threshold thing, so Wenchun, if you could just go to this section, there is a very good description of this one, precision recall trade-off. Can you go to this section?
Sorry, which section? Which page?
The precision recall trade-off. So there is this picture with the images where there are some handwritten digits. Yeah, go up, keep going up. Exactly, this one.
Okay.
So this is a very good explanation, I think, of the threshold. So here they practically show how the threshold influences the whole thing. If we keep the threshold at the middle, we can see there is some precision and recall, and the confusion matrix and everything regarding this true positive, false positive, everything depends upon these two things. Like what is the precision, what is the recall. On top of that, we create the confusion matrix. So there is a very good explanation on the if you keep the threshold on the middle, then it is showing precision has some value, recall has some value. Then if we change the threshold to the right, then those things are changing accordingly, because we can see some false positives are going out, some true negatives are coming in. This kind of things happen. So this is how threshold actually influences the whole precision recall thing, which in turn influences the true positive rate, false positive rate, that influences the rest of the thing. So this is, I think, a good explanation of that.
Absolutely. Thank you. Cool. Anyone else? This is also a great graph, you know, when you shift
how
like thresholds.
How threshold influences the precision recall. It's a great. So basically from here, as they have shown there, from this curve only they first decide. Say for example, what this explains is that there we can see two red dots there. So on the top dot, the statement here that they worked upon is that first they want to achieve 90% precision. So first what they did, the blue dotted line, that is a precision curve. From that curve, they decided which point is the 90% on this curve. That is the top red dot. From there, they decided the threshold for this one is something around 8,000 or something like that. Then it drew a vertical line from there. Then they detected where that vertical line is cutting off the recall. Depending on that one, they are deciding that this is the recall that I'm going to get. Now, if we change the threshold, if we think it the other way, if we change the threshold, that is in turn going to affect the precision and recall as well. So this is how the threshold affects the whole thing.
Cool.
Yeah, and this illustrates the thing I said before, that the precision and recall curves are parametric curves that can be calculated in terms of threshold. In other words, threshold is the independent variable,
Right.
and precision and recall are dependent variables.
Yeah.
And I think when you have imbalanced classes, you tend precision recall curve tends to be more helpful than ROC curve, which is more used in the scenario that when you have like balanced classes. Cool.
So regarding that one as well, there is a in our current reading we will see there is one line that they, one sentence that they make a comment upon in this ROC curve, where when to use the ROC and when to use the PR curve, right? So you can find that comment right after the ROC curve. If you keep going in the ROC curve, there is a statement that they make inside the tip section. Since the ROC curve is so similar to the PR curve, you may consider how to decide which one to use. As a rule of thumb, you should prefer the PR curve whenever the positive class is rare, or when you care more about the false positive than the false negative. Otherwise, use the ROC curve.
Right.
Yes.
There's a tip. We'll get to that in a bit. Thank you. Anyone else on the ROC? Not no one is following the concept? Cool. Okay. So, and this is how the FPR and TPR looks like. And FPR, TPR should range, between 0 and 1, and thresholds is just everywhere. Cool. And with the ROC curve, you're just plotting FPR, TPR, false positive rate, and true positive rates, and and this is basically writing a function to plot this, and I think this is pretty straightforward in terms of just plotting this. And look at this diagonal line. I just kind of want to just have everyone pay attention to that. This diagonal line, what does this mean? It means when you're on this diagonal line, your true positive rate is exactly equal to false positive rate. And I kind of want to also mention a couple of different points, like what does this mean? What does it mean when we are here? What does it mean when we are here? What does it mean when we are here? What does it mean when we're here? So when we are here, that means true positive rate is 1, and false positive is also 1. That means we're correctly classifying all the true samples, and incorrectly classifying all the false samples. And in other words, we're doing great on the y-axis, on the true positive rate, but we're not doing so great on the false positive rates. Now, when we are here, that means our true positive rate is 0, and our false positive rate is 1. That means we're incorrectly classifying all the true samples, and we're incorrectly classifying all the false samples. So we're actually doing everything wrong, pretty much. And when we say ROC curve, we want to be as upper left as possible. And why is that? Because that's when the true positive rate is 1 and false positive rate is 0. And what does that mean? That means like when we're correctly classifying all the true samples and we're correctly classifying all the false samples. And that's why like when if the ROC curve is further upper left to the upper left direction, that means your algorithm is doing great. And I think, you know, for the sake of time, I think now people should understand what does it mean when you have 0 on the true positive rate and 0 on the false positive rate. Is that clear?
Just one piece of clarification on this. So you will, like, when you run an experiment and test the results, you'll end up at one specific point along this curve. And obviously, as you tweak things, you can move up and down that curve. But it sounds like at the end of a test, you'll have a certain amount of true positives and a certain amount of false positives, right?
Correct. If you look at, it's like here.
Right.
When you move your thresholds, it creates a bunch of dots. But you know, if you have a very smooth line, then you know those dots go away. It becomes a way much smoother line.
But will you end up at one specific point? Like the result of validating some model will ultimately end up at one point?
Well, you would want to pick this point or this point because that actually maximizes the area under curve rather than this point or this point.
But it's correct that every time we feed to one particular model, we are just having a particular threshold selected. We might be or not aware of what the threshold is, but that just represents one point in that ROC curve. So in reality, we'll have to use different thresholds. So if you linearly try all the thresholds, then you can reconstruct the curve. But yes, you're right that each model that we feed is only one point in that curve.
So my 2 cents on this one, what I understand is that the asker is doing commenting the right thing. So eventually we will land up on one point on that ROC curve. The reason being, initially we are trying out different model parameters and everything, and we are checking the F1 score and everything. Eventually we are zeroing on one particular score that yes, this is the score that is acceptable to me. That score refers to one particular false positive rate, false negative net, like 2 positive, 2 negative, those value, one particular values for all this. Because we are selecting one particular F1 score that is acceptable for me. That corresponds to one particular 2 positive, 2 negative, that by default corresponds to one particular threshold, because that 2 positive, that 2 negative, etc., that is regarding one particular threshold. So when we decide on one particular threshold, we are by default pointing to one particular point of the ROC curve. So eventually, after all this drama, we will left with one particular point on this ROC curve. That is my understanding.
Right. I agree. And in the end, it also depends on your business use case, right? Because you might want a higher true positive rate, or you might want a higher false positive rate. And
so there is one section which talked about that one. So there was one example that filtering of the shows or videos that is shown to the baby. So for that case, true positive is more important than false. The example was true positive is more important than false positive. So their intention was to increase the precision rather than the recall. So for that, the threshold will be quite high. There was another use case of detecting shoplifters. So for that case, the recall is more important than the precision, because they want to detect as many people as possible. So in that case, recall was more important than they taken down the threshold. So in that case, threshold is low. So it definitely depends upon the use case.
So, and if you don't have a particular use case, then another thing you could do is try to find the threshold that gives you a point on that operating curve that's closest possible to the top left corner. So basically just run through the entire, could you go back to where the ROC curve is, Wencheng? Yeah, so you could basically run through and create that whole curve and then find the point on that blue curve that is closest to the top left corner. And that will be, in some sense, an optimal operating point.
Right.
Is that optimal operating point provided to you in terms of like use these hyperparameters to achieve that upper leftmost point?
No, you actually determine it yourself by running through all the possible thresholds, calculating that blue curve, and then just locating on that blue curve the point that is closest to the top left corner. And so that tells you where you should set your false alarm, your false positive rate, and your true positive rate to be at that optimal threshold.
So you can probably use something like np.rmax or one of those things, and you can automatically find out what that value is.
Sure.
And the other point is like how Wenchang mentioned the top left is what you want to achieve. I think it's the same with if you end up with the bottom right, if you end up with like 0,1, that also means you have a great model. It just means that you unintentionally inverted the positives and the negatives.
Yeah.
So it still means that you have a great model. You just swap those things out.
Yeah.
This is one question that I had. So specific this question. So they always talk about this one. They always make the statement that try to make the curve as close to the top left possible. But as Wencheng described, it is as good as you said, it is as good as the model if we take it closer to the bottom right, right? So it is not always like that. Try to make the model top left.
I didn't quite understand what the previous person was saying when you said if
Like
we're here, it's also a good model.
Right. What you mentioned, Wenchang, you actually mentioned that you're making an error both on your true negatives and the other one, right? So you're making a double negative. So what happened was you were supposed to say, okay, classify this group as 1. Those are the people who are, let's say, fraudulent transactions. And the non-fraudulent transactions, ideally, you wanted to make it 0. You built your model out. You swapped those two for some reason by mistake. So now everywhere where your trues were actually zeros, your actual predicted values will be exactly opposite of that. And that's why you're getting this opposite thing. So all you have to do is just do like naught of that, and you'd again end up with a perfect match, right? Does that make sense?
Got it. Okay. Okay.
So but that's an error on your end, nothing with respect to your model. I mean, that is something I've run into experience, so that's why I wanted to kind of share.
Got it. Okay. I see what you're saying. Cool.
Regarding my question, so it is not regarding that this blue curve, we have the intention should be to make the blue curve only towards the left top. Oh, that should not be the only intention. The actual intention should be to make the curve as far away as possible from that diagonal line. That is
true. That is true. But if you were to do everything correctly, then your ROC is always that curve is always going to be above than 50%, right? So that's why area under the curve will be greater than 50% if you do everything correctly until and unless you do a mistake. But otherwise, what you're saying is right. You can look at area under the curve if you just flip the diagram the other way around. That's why what you're saying also makes sense.
Right.
So yeah.
So that is the point. So in that case, if I flip the diagram, in that case, the area under the standard definition of area under the curve is that from that, what should I say, the horizontal and vertical line, 0, 1, and 0, 1, that is the area. So if I just flip the curve, in that case, mathematically, the area under the curve is going to be very low.
Yes.
But even in that case also, it is a good model.
Right.
So area under the curve, we can't take it, like we have to take it with a pinch of salt, right?
Right.
Okay.
Okay, so let's keep going.
Yeah, if area under the curve is significantly less than 0.5, that tells you that you've made an error. As Rekil said, you switched your classes. So all you have to do then is switch the classes back, and then your area under the curve will be bigger than 0.5.
Right, understood.
Okay, so once again, there's a trade-off. The higher the recall TPR, the more false positive the classifier produces. The dotted line represents the ROC curve of a purely random classifier. A good classifier stays as far away from that line as possible. I think we just mentioned that towards the top left corner. Okay. One way to compare classifier is to measure the area on the curve, AUC, a perfect classifier will have a ROC AUC equal to 1. And I think he was just referring to ROC AUC score. Whereas a purely random classifier will have a ROC AUC equal to 0.5. Scikit-learn provides a function to compute ROC AUC. I was trying to find the exact exactly how Scikit-learn calculates this, implements this, and I was in the GitHub folder of Scikit-learn, but I couldn't understand the way how they calculate. Anyone has some ideas how this is calculated?
There are standard methods of finding the area under the curve, right? I mean, I think Simpson's rule is one. I mean, you know, if you try to remember back in your calculus class, you know, or if you didn't take calculus, what you do is you start constructing small vertical rectangles, right? And you take and you sort of add and that intersect the curve, right? And then you try to add up those rectangles, and then the smaller the rectangles are, the closer you'll get to the right answer. So it's just basically a numerical technique of integration. That's all that routine is doing. It's just doing the integral under the curve, the area under the curve. Yeah.
Cool. Thank you, Joseph. Great. So tip, since the ROC curve is so similar to precision recall curve, you may wonder how to decide which one to use. As a rule of thumb, you should prefer the PR curve whenever the positive class is rare, or when you care more about the false positives than the false negatives. Otherwise, use the ROC curve. For example, looking at the previous ROC curve and ROC AUC score, you may think the classifier is really good, but this is mostly because there are few positives compared to the negatives. In contrast, the PR curves makes it clear that the classifier has room for improvement. The curve should be closer to the top right corner. So this ties back to like ROC curve might not be the best choice when you have imbalanced classes. Okay. Let's now train a random forest classifier and compare its ROC curve and ROC AUC score to those of the Sgd classifier. First, you need to get scores for each instance in the training set, but due to the way it works, the random forest classifier class does not have decision function method. Instead, it has a predict proba methods. Scikit-learn classifiers generally have one or the other or both the predict proba. And we tried this, right? Like Sgd classifier with SVM doesn't have this. The predict proba method returns an array containing a row per instance and a column per class, each containing the probability that the given instance belongs to a given class, 70% chance that the image represents 5. So let me try to think this is what we got in terms of the score. This is what I had. Okay, so basically, he was just using this lines and to feed into it. The score equals the probability of positive classes, Y probas, forest. This is probably of negative classes. So we only want the positive classes, probability of positive classes. And then we feed that into the ROC curve. Cool. So the ROC curve function expects labels and scores, but instead of scores, you can give it class probabilities. Let's use the positive classes probability as the score, and that's what it is. The index 1 column is the probability of positive classes. Index 0 column is the probability of negative classes. Now you are ready to plot the ROC curve. It's useful to plot the first ROC curve as well as to see how they compare. So we're trying to basically compare the ROC curve of the SGD or SVM underneath that, and the random forest classifier, and see which one is better. Cool. So, and we're basically the dotted line is the SGD, and the solid line is the random forest, and we're just basically plotting them on the same graph. As you can see, the random forest classifier's ROC curve looks much better than the Sgd classifiers. It comes much closer to the top left corner. As a result, its ROC AUC score is also significantly better. Again, I was just like pretty much trying to see what's going on in the variables, and this is the plots. And this should be the ROC AUC score from the random forest classifier. It's 99, 0.9983. So cool. Try measuring the precision and recall scores. You should find 99% precision and 86.6 recall. Not too bad. Now you know how to train binary classifiers, choose the appropriate metrics for a task, evaluate classifiers using cross-validation, select the precision recall trade-off that fits your needs, use ROC curve and ROC AUC scores to compare various models. Now let's try to detect more than just the fives. Okay, so let me take a pause. Anyone has any questions up to this point? We good? Okay. Multi-class classification. Whereas binary classifiers distinguish between two classes, multi-class classifiers, also called multinomial classifiers, can distinguish between more than two classes. Some algorithms, such as logistic regression classifiers, random forest classifiers, and naive Bayes classifiers, are capable of handling multiple classes natively. Others, such as Sgd classifiers or support vector machine classifiers, are strictly binary classifiers. However, there are various strategies that you can use to perform multi-class classification with multiple binary classifiers. One way to create a system that can classify the digit images into 10 classes from 0 to 9 is to train 10 binary classifiers, one for each digit. And then when you, a 0 detector, a 1 detector, a 2 detector, and so on. And then when you want to classify an image, you get the decision score from each classifier from that image, and you select the class whose classifier outputs the highest score. This is called the one versus the rest strategy, also called one versus all. Cool. Another strategy is to train a binary classifier for every pair of digits, one to distinguish 1 and 0 and 1s, another to distinguish 0s and 2s, another for 1s and 2s, and so on. This is called the one versus one strategy. If there are n classes, you need to train n times n minus 1 divided by 2 classifiers. For the minutes problem, this means 45 binary classifiers. So that's basically 10 times 10 minus 1, that's 9 divided by 2, 4.5 times 10, that's 45 binary classifiers. When you want to classify an image, you have to run the image through all 45 classifiers and see which class wins the most dues. The main advantage of OVO is that each classifier only needs to be trained on a part of the training set for the two classes that it must distinguish. Some algorithms, such as SVM classifiers, scale poorly with the size of training sets. For these algorithms, OVO is preferred because it's faster to train many classifiers on small training sets than to train few classifiers on large training sets. for most binary classification algorithms. However, OVR is preferred. Okay, and OVR stands for that's one versus the rest. That's basically training a bunch of binary classifiers. Okay. Scikit-learn detects when you try to use a binary classification algorithm for a multi-class classification task, and it automatically runs OVR or OVO depending on the algorithm. Let's try this with a supported vector machine classifier using these scikit-learn, SVM, SVC class.
Can I
Okay.
just interject something here?
Yep, go ahead.
I'm curious because, you know, I'm used to one versus rest, but not one versus one. Is this a well-known computational hack, or is this something that just kind of got grandfathered in because I've not run across it before, but it might just be scikit-learn? Anybody have an idea or an opinion?
I haven't used that either. Anyone else has ideas? No? Okay. Well, I guess we'll probably have to look it up.
I mean, I can say something about this. So,
Sure.
so they're both known, but yeah, the most commonly used one is one versus the rest. The one versus like what they called here, was it OVO? Yeah, that's also common, but I wouldn't say OVR is definitely more used than OVO, but yeah, they're both known. So yeah, it's something that you would specify, I guess, on the algorithm, which one here on scikit-learn that you want to use. But yeah, OVR is the most common one for sure.
And I think when you come to like a large data sets, you almost just like start doing neural networks. And so I don't think this, you know, even is applicable nowadays, right? This kind of decision.
So I had a couple of questions on this possible maybe use cases or applications. I was planning to do something like this, but I was wondering if somebody else has already done this. So the first one is it possible to use the one versus one, a binary classifier, when I'm doing a multi-class problem, just to overcome class confusion between two classes? Suppose I look at a confusion matrix and I see that a couple of classes are mostly confused with each other. Is it then possible to then just train a model with just those two classes, with the one versus one, and then would I be able to achieve a better accuracy? And if so, is it then possible to ensemble that to achieve like an overall better classifier?
Anyone has answers?
From a practical standpoint of things, like you'd have to run two models at inference. So that is the only reason why I can think that you would want to avoid something like that.
Okay, but like at a basic sense, does is anything helpful for the model to see only two classes, which will help it achieve better accuracy versus like a number of classes?
Let's say you have like n number of parameters, and I'm just thinking out loud here. Let's say you just have n number of parameters and you're doing like one versus one, versus if you do like the 10 class thing, you would assume, I mean, I would think that those n parameters are trying to learn to distinguish 10 classes, versus you're using those n parameters to distinguish only two classes. Maybe it would help, I'm not sure. But at the same time, you're looking at the same images on both your runs, right? It's not like you're seeing different images on both your runs.
Right.
So maybe a strategy like pre-processing or something would be more fruitful. I don't know.
Okay.
It doesn't. I mean, in practice, shouldn't we just start using like neural networks or softmax to handle a problem like this? I mean, from a practical standpoint, instead of like trying like OVR or OVO. Anyone?
I guess at the end of the day, you try everything, and whichever works best for you. Yeah.
Yeah, neural networks do not always outperform, especially tree-based methods and ensemble methods. So yeah, it depends on what the problem is. And sometimes, as Jeremy found in that store, I think there was a store problem that he used, Germany, grocery store problem in Germany, and he found that without any specialized domain knowledge, he could use a neural network to beat the random forest and other ensemble methods, but this is not always going to be the case. Sometimes domain knowledge really helps you to construct features that really make a high score.
Yeah, absolutely.
And just to add, I think he's talking more about these two because he's using SVM here, and that's why, yeah, he wouldn't talk about this if he's talking about neural networks. So, but it is valid to talk about him if he is using SVM. And yeah, and as Joseph just said, there are cases where just an SVM may be of a better use than neural networks. Not necessarily just on the accuracy, but maybe it can be maybe faster, or depending on the case. So yeah.
Cool.
Yeah. One thing that I've found that for instead of using softmax, if you want more interpretable, like single class threshold values, a more sigmoid type is better than softmax.
Sure.
Otherwise, you're dealing with the prediction being weighted in between the various classes so that they all add up to 1.
Sure. Yeah. Of course. Cool.
So the only thing, as I think somebody mentioned, the only thing here to keep in mind is, yes, what if we have like a large number of classes? I think that makes the point of then there's going to be a difference between uses 1 versus 1, and which going to be so much more than just using 1 versus the rest. And exactly, I think somebody just gave a number of like, say 10, or what if you have maybe even more number of classes?
Cool. Anyone else? Okay, so let's keep going. That was easy. So right now we're not just doing 5s or not 5s. We're doing all 10 classes, right? So we're just pulling Y-train instead of Y-train 5, and we're just feeding that into SVC. I'm curious, do you guys know the difference between like just calling this and Sgd doing the default option with SVM? Any difference?
I think SVM has deterministic methods to find a solution. I forget what they're called, but you can look that up when you look up SVM. There are different methods to use for the solver, and there are very good solvers for SVM problems. So when you use Sgd together with SVM, that's saying, let's not use the solver, let's not use the deterministic solver, let's just use the stochastic gradient descent, the simple stochastic gradient descent method to find the solution.
Got it.
And I don't know, sometimes that might be faster, or it might be more accurate. I don't know what the trade-off is.
Got it. Cool. Okay, so that was easy. This code trains SVC on the training set using the original target classes from 0 to 9 instead of the 5 versus the rest target classes, 5 train 5, and it makes a prediction a correct one in the case. Under the hood, scikit-learn actually used the OVO strategy. So even though we don't see that here, but it actually uses 1 versus 1 strategy because we're using SV. I think because we're using SVM, it trained 45 binary classifiers, got their decision scores for the image, and selected the class that won the most dues. If you call the decision function method, you will see that it returns 10 scores per instance instead of just one. That's one score per class. So basically that's 0, 1, 2, 3, 4, 5, all the way to 9. And this one is the highest. So we pick that, and that's the basically number 5, or the number 5 class. And that's basically just returning the highest number with its index, and that's 5. Cool. So warning, when a classifier is trained, it stores the list of target classes in its classes underscore attributes ordered by value. In this case, the index of each class in the classes underscore array conveniently matches the class itself. But in general, you won't be so lucky. Okay, so be careful when you do this, because we're dealing with MNIST right now, so it just happens to match. But just be careful when you deal with other use cases.
So in such a case, like I've noticed, like at least when I am working on a different case, suppose I have names for my classes, like and it is essentially sorting it and putting it together. So for me, when I'm wanting to decode it during prediction, it's good for me to actually look at that classes underscore array once to see what's going on. Otherwise, it's just indices. And then I actually plotted my confusion matrix without sorting the labels first, because I thought it will be in the way I gave it in my original data frame, but it was not. So my confusion matrix was all wrong. And then I actually went and looked at this, and then I understood.
Cool. Thanks for sharing. Anyone else? Okay. So if you want to force scikit-learn to use 1 versus 1 or 1 versus rest, you can use 1 versus 1 classifier or 1 versus rest classifier classes. Simply create an instance and pass a classifier to its constructor. It does not even have to be a binary classifier. For example, this code creates a multi-class classifier using OVR strategy based on SVC. So you can even just like feed this SVC class into this 1 versus rest classifier and kind of forcing it to do like 1 versus rest. And I didn't know we could do that. So this is pretty interesting to see. Okay, training an Sgd classifier is just as easy. And you're basically just, yeah, this is pretty straightforward. Okay. I was looking up this gamma. It's a kernel coefficient of SVM. And sorry. Okay. Yeah. And when it's auto means like 1 divided by n features, that's the kernel coefficient to pass into the SVC. Cool. And again, you get the decision function. I'm not running those codes because a lot of those fit and predict take a lot of time to run, and I almost thought like my machine was just stuck, especially with that KN. It took a long time to run, so I kind of just interrupted my kernel at that time. And for the sake of the class, so I'm just not running some of the code. Okay. And again, this is just 1 versus rest classifier, as we saw here. Cool, so let's keep reading. This time, scikit-learn used the OVR strategy under the hood. Since there are 10 classes, it trained 10 binary classifiers. So basically, I think it was using OVO by default, but you can force it to use OVR. Then now, since there are 10 classes, it trained just 10 binary classifiers instead of 45 binary classifiers. The decision function method now returns one value per class. So again, this is the highest, even though this is also close or positive, but it still picked the right one. You can see the classifier is fairly confident about its prediction. Almost all scores are largely negative, while class 5 has a score of 2412.5. The model has a slight doubt regarding class 3, which gets a score of 573.5. Now, of course, you want to evaluate this classifier. As usual, you can use cross-validation and use the cross-val score function to evaluate the Sgd classifier's accuracy. So, and he did 3 votes. So you get basically three scores. It gets over 84% on all test votes. If you use a random classifier, you get 10% accuracy. I think it's just because there are 10 classes, so you get 10% accuracy. So this is not such a bad score, but you can still do much better. Simply scaling the inputs, as discussed here, increases accuracy by 89%. Now, standard scalar is basically minus your mean divided by standard deviation, so that you kind of just scale all your numbers to have a mean of 0 and within a certain range as well, and that performed better in this case for the MNIST data sets. Okay, before we jump into error analysis, anyone has any questions?
I'm just trying to get an intuition as to what it actually means when we are scaling images. These are pixel values. Those are the numbers that we're standardizing here, right? Per pixel value, and then we are scaling it to be between certain values.
Just scale, just pixel values. And also with neural networks, you would also have to squash them between like -1 or 1 or 0, between 0 and 1, I forgot. And because of the vanishing or exploding gradient problem.
Right. I mean, here in this case, like with values being between 0 and 255, I'm trying to understand exactly by scaling it, will it not alter the images such that they kind of get squished too much?
You wouldn't be able to display them until you translate them back, because standard displays are expecting the pixels to be between 0 and 255. But that's just for display. It does look to me like they should have used normalizing here instead of standard scalar, because this could have, the data could have negative values and it could have values. I mean, I think what you really want to do is put the numbers between 0 and 1. So you just want to scale it down by a factor of 255. But I guess this works too. And I wouldn't have done it that way.
Just looking at standard scalar on the scikit-learn page, and it seems like this is normalization.
Yes, it divides by, it subtracts mean and then divides by S,
Exactly.
That's not the same, because what that does is it makes the distribution to have mean 0 and and standard deviation 1, which means that you could have negative values. If you have a distribution centered on 0, then you can have negative and positive values. But if you normalize instead, which means let's see, it means subtracting the the minimum value, and then dividing by the maximum minus the minimum value, that is scaling it, and then adding back the minimum value.
Right.
That's the way that you would sort of squish the values between 0 and 1. It seems to me that that would be the more reasonable way to do this, but it apparently doesn't matter too much. So as long as you get it in a standard, so that all of the features are having the same mathematical properties.
Is there any reason you think this is better than -1?
Talking about this, Joseph, that actually reminded me, actually, one time I was comparing how normalization done, like between PyTorch, I believe, PyTorch and TensorFlow. And if you go and if you see, for example, if you take like how, for example, you're gonna use the pre-trained ImageNet and how they did normalization on that, you will find that that one of them, I'm not sure which one. So PyTorch actually used this one, that everything is between, is that the mean is 0 and unit values. PyTorch, they used kind of like this scaling that we're looking at right now. But when you go to TensorFlow, actually they use a different kind of normalization. And so that's something that I vividly remember, and I'm not sure why they're doing it. They have it both different, but it's just something to be aware of,
Yeah, that's interesting. I think if you, perhaps if the pixel values have closer to a normal distribution than a uniform distribution, then it might make sense to do the scaling, the standard scaling, the standardization, I mean, instead of the normalization.
Yeah, one thing I've ran into this is actually if it's not centered around 0 and you're using FP16, a lot of the times your model won't even train because you have more precision near 0.
Oh, that's a good point. I've encountered things like that too, where the model prefers that you center it on 0. So yeah, that's a good point.
I don't think it's so much to do with the pixel values per se, right, Joseph? It's more to do with you want the pixel values to be centered at 0 so that your weights can also be like around there. So scaling it, I think between like subtracting the mean and dividing by standard deviation is what kind of makes sense. And talking to Salim's point, like, I don't think you can use transfer learning and kind of do like a different subtraction of mean and division by standard deviation and kind of expect the same output.
No. You have to do
That's not going to work.
You have to use the exact same normalization that was used in creating the model. Yeah.
Right. So.
Exactly. That's the whole point. So when you use the ImageNet stats of your pre-trained model, so if you go back to ImageNet, how they got the stats of ImageNet in PyTorch and TensorFlow, you would find that they got them in 2 different ways. One was just they're using the scaling that we're looking at, and the other one was using normalization. And I agree with you with that point. But that was just, I remember that was confusing when I found that they were different.
So I visualization to compare the standard scalar and min-max scalar. This is the data after standard scaling with median income and number of households. And look at like when it compares to like min-max scalar, this is the data after min-max scaling. Pretty interesting. Cool. Okay, anyone else?
I guess the min-max scaling automatically sort of chops, it automatically takes care of outliers. There aren't any big outliers, whereas when you use standard scaling, it's possible to get outliers that are well away from the mean.
Right.
But, yeah.
I think
anyway,
that's
yeah,
a fair reason, right? Like when we were doing median income, you could have outliers, so that's why you kind of go with the min-max approach. Whereas in pixel values, you know they have to be bounded between 0 and 255. You cannot have them outside that range.
Good point.
So maybe that is something we can kind of look into more and see. Maybe that's a reason.
Good point.
But that's a really interesting observation that Salim made, that that TensorFlow and PyTorch give differently normalized pre-trained weights for ImageNet. That I didn't know.
Cool. Okay, so let's keep going. Running short on time. Error analysis. If this were a real project, you would follow. You would not follow the steps in your machine learning project checklist. You would explore data preparation options, try out multiple models, shortlisting the best ones and fine-tuning their hyperparameters using grid search CV, automate as much as possible. Here, we will assume that you have found a promising model and you want to find ways to improve it. One way to do this is to analyze the types of errors it makes. First, look at the confusion matrix. You need to make predictions using the cross-val predict function, and call the confusion matrix function just like you did earlier. This doesn't have labels, but if you want to kind of get an intuition of what's going on, I've kind of found this, like with multiple classes, like it's basically you have the predicted labels here and the true actual labels on the top. And what does it mean? Like it just means like when you predict this to be cat, and it's also actually cats, and then we got 4 here. So basically when the predicted matches the actual, that's on the diagonal line, and when the predicted doesn't match the actual, you are off the diagonal. So, and that's what it is. Basically, this is 0 to 9, and this is 0 to 9, and the diagonal has basically just tells you like number of cases that the predicted matches the actual samples.
One thing here.
Yep.
The diagram that you are showing and this confusion matrix that they have printed here, just one thing is that it is reversed. So here in the picture, the true part, the true classes are in the columns and the prediction are in the rows. But in this confusion matrix, it is just the reverse. So the rows are the actual classes and the columns are the predictions.
Got it. Cool. Thank you for bringing that up.
Sure.
Okay. There's a lot of numbers. Let me just go back to the code. And he kind of also visualized it. I don't know why he used grayscale, but I guess it's clear to use that. It's often more convenient to look at an image representation of the confusion matrix, and he did write just that. And this confusion matrix looks pretty good since most images are on the main diagonal, which means that they were classified correctly. Again, when you're on the main diagonal, that means it's good. It's classified correctly. The 5s look slightly darker than the other digits. The 5s here, it's slightly darker, which can mean that there are fewer images of 5s in the data sets, or that the classifier does not perform as well on 5s as on other digits. In fact, you can verify that both are the case. Let's focus the plot on the errors. First, you need to divide each value in the confusion matrix by the number of images in the corresponding class so that you can compare error rates instead of absolute number of errors, which would make abundant classes look unfairly bad. Fill the diagonal with zeros to keep only the errors and plot the results. And you can clearly see the kinds of errors the classifier makes. Remember that rows represent actual classes. So yes, so basically the rows now are the actual classes, rather than, here, the rows are actually predicted, so it is reversed. While columns represent predicted classes, the column for class 8 is quite bright. and that's this column, which tells you that many images get misclassified as A's. However, the row for class 8 is not that bad, telling you that actual A's in general get properly classified as A's. So this is actually not that bad, but this is actually quite bright, which tells you many images get classified. So basically, when the model is trying to classify the images that are A's, it got to a pretty good accuracy, but like it misclassified many other images to be the A's. So that's not doing well. As you can see, the confusion matrix is not necessarily symmetrical. You can also see that 3s and 5s often get confused in both directions. So 3s is here and 5s are here. So we can see some bright spots here. 3s, 5s, okay. And analyzing the confusion matrix often gives you insights into ways to improve your classifier. Looking at this plot, it seems that your efforts should be spent on reducing the false A's. For example, you could try to gather more training data for digits that look like A's but are not. So that I guess that's one of the ways to kind of add more data, and so that the classifier can learn to distinguish them from real A's. Or you should engineer new features that will help the classifier. For example, writing an algorithm to count the number of closed loops. 8 has 2, 6 has 1, 5 has none. Or you should pre-process the images using scikit-image, Pillow, or OpenCV to make some patterns such as closed loops stand out more. This is pretty interesting. I've never done this before, but I'm curious to hear if anyone has some practical experience on this.
So Wang Chang, I have a question.
Yeah.
I was going to ask the same thing. If anyone has an experience coding how to count the number of loops that each figure would have, or perhaps knows how to use Pillow or OpenCV to check the number of closed loops.
You mean like, were you trying to ask basically how is it done?
Yeah, how it's done.
Yeah,
that seems a bit beyond me.
Yeah, I mean, I guess you can, in some ways, I'm just thinking about it because I haven't done it, but like really kind of try to detect how many loops, like writing, it's almost like writing, I would say like a classifier, and just to kind of classify images with how many loops you have.
Some basic, sorry to interrupt.
Yeah, no, go ahead.
For some basic pre-processing in images can be done with OpenCV, where you can use some filters, so that will it will make the darker pixels more darker and the lighter pixels more lighter. So that way you get a boundary between things, and that way you can easily carve out edges, and in similar fashion get a loop also. That's one idea.
Yeah, OpenCV has a bunch of functions called like half circles and stuff like that, which can look for circles. The tricky thing with that is like, even if there's like a single line of pixel missing, even though it's visually not seen, it will look like probably a circle to you. But then since it's a computer, it's not going to find that. So that means you're expecting your user, whenever he writes a 6, to complete that circle completely. So I think it comes with pros and cons if you want to use something like that.
Cool. Thank you for sharing that.
One little tweak that one could do is when you look at that confusion matrix, and you see that true 5s are often miscategorized as 8s, you could make your detection threshold for a 5 higher so that it will be less likely to make a mistake like that.
Cool.
And
Analyze. Yeah, go ahead.
Sorry, in the current situation, you cannot set a threshold for a single number, right?
If you do OVO classification, you should be able to.
If you end up with that, right?
Yeah.
Cool. Analyzing individual errors can also be a good way to gain insights on what your classifier is doing and why it's failing, but it's more difficult and time consuming. For example, let's plot examples of 3s and 5s. The plot digits function just uses matplotlib's show function. See this chapter's Jupyter Notebook for details. So basically, I mean, these two are all correct, right? Like correctly classified. So basically, but this group is classified as 5s, but are 3s. So they're actually just 3s, but they're classified as 5s. And this group is classified as 3s, but are really just 5s. So those two are correctly classified, and those two are not. Cool. The two 5 blocks on the left show digits classified as 3s. Again, those are actually just 5s, but classified as 3s. And the 2 5 blocks on the right show images classified as 5s. Some of the digits that the classifier gets wrong in the bottom left and top right blocks are so badly written that even human would have trouble classifying them. For example, the 5 in the first row and second column, the 5 in the first row, and second, this one, right? And it truly looks like a badly written 3, but it's actually a 5. However, the most misclassified images seem like obvious errors to us, but it's hard to understand why the classifier made the mistake it did. The reason is that we used a simple Sgd classifier, which is a linear model. All it does is assign a weight per class to each pixel. When it sees a new image, it just sums up the weighted pixel intensities to get a score for each class. So since 3s and 5s differ only by a few pixels, this model easily confused them. Anyone wanted to say something? Did I hear something? Okay. The main difference between 3s and 5s is the position of the small line that joins the top line to the bottom arc. If you draw a 3 with a junction slightly shifted to the left, the classifier may classify as so basically a junction here, right? So if it's 3 shifted more towards the left, then if it's more likely to be like 3, and if it's here, then it's more likely to be a 5, vice versa. In other words, the classifier is quite sensitive to image shifting and rotation. So one way to reduce the 3-5 confusion would be to pre-process images to ensure that they're well-centered and not too rotated. So that comes with image augmentation, I guess. Any thoughts? Any further thoughts on this section? No? Okay. Let's keep going. Multi-label classification. Until now, each instance has always been assigned to just one class. In some cases, you may want your classifier to output multiple classes for each instance. Consider a face recognition classifier. What should it do if it recognizes several people in the same picture? It could attach one tag per person and recognizes. Say the classifier has been trained to recognize 3 faces, Alice, Bob, and Charlie. And when the classifier is shown a picture of Alice and Charlie, it should output 101, meaning Alice, yes, Bob, no, Charlie, yes. Since the classification system that outputs multiple binary tags is called a multi-label classification system. We won't go into face recognition just yet. We'll just look at a simple example just for illustration purposes. This is basically creating basically trying to first indicates whether or not the digit is large. So basically that's a condition on the labels. And the second indicates whether or not it's odd, and that's another condition. Divided by 2 equals 1. And the next line creates a k-neighbors classifier instance, and we train it using the multiple targets array. Now you can make a prediction. Notice that it outputs 2 labels. Cool. Let me just go through the code. Yeah, so this was the one that took a lot of time, and I just kind of interrupted. So make sure, you know, if you want to try, just, yeah, make sure you have some time, you know, to be available to train this. Cool. And I get to write. Yeah.
One point to note here. So basically a question here. This, whenever I try to run this cross-val predict function, it is taking awfully lot of time. So even if at the end of the section they have explicitly mentioned that a warning that if you want to run this cell, be prepared to spend some couple of hours on this one. So is
Yeah.
it that cross-val predict function is inherently slow, or is it that there is so much of data, or are we are dealing with the image data? So what is the reason for this one? Any idea on that? Why cross-val predict function is so slow?
My sense has to do with the KNN, but I want to hear if anyone else has thoughts on this.
Okay, so you are thinking that it is not because of the cross-val predict function, rather the algorithm that we are passing. So had
Right.
I passed some other algorithm, probably it would have run faster.
Yeah, and in this case,
Yeah,
it's
we do use cross-val predict up higher in the notebook with a different algorithm, and it's fine. So I would say it is the KNN that's causing the delay.
Okay. Okay. Thanks.
Okay. Okay, there are many ways to evaluate a multi-label classifier, and selecting the right metric really depends on your project. One approach is to use the F1 score for each individual label, or any other binary classifier metric discussed earlier, then simply compute the average score. This code computes the average F1 score across all labels. So you basically just do an average operation among the F1 scores you get. Cool. Let's assume that all labels are equally important, however, which may not be the case. So I guess, you know, in some use cases, not all labels are equally important. In particular, if you have many more pictures of Alice than of B or Charlie, you may want to give more weight to the classifier's scores on pictures of Alice. One simple option is to give each label a weight equal to its supports, the number of instances with that target label. To do this, simply set average equals to weighted in the preceding code. So basically just change this to weighted.
So what does macro do actually, as opposed to weighted?
That's a good question. Let's take a look.
So macro is basically going to weight it by the number of classes. So let's say you had 4 classes. It's not going to look at the number of samples.
Okay.
So you could have like completely imbalanced classes. You would calculate each of the scores independently and then divide by number of classes. So basically, it's trying to tell you that pay more concentration on the one which has more number of samples, which could be the result you want, which could not be the result you want. Weighted, on the other hand, would do weighting on the number of classes, number of samples in each of the class.
And then there is micro as well,
micro
which
also, right.
Does
I was just,
the raw calculations.
Yeah, I was trying to kind of get an intuition as to the applications of each of them, as to in which situation you'd use which one. Because I've seen in cases of imbalanced data sets, the actual like the competition or someone actually recommending macro, even though it is imbalanced. So I don't know what the objective there is in that case.
Yeah,
Why
I
not?
have seen
Why
that.
not?
I have seen that as well, and there's no clear explanation given of why they chose that versus the micro
weighted,
or
for
weighted.
example. Yeah. Okay.
I think one of the reasons, like if you look at it, is if you have 3 classes, you specifically are the organizers of the competitor are saying that I want more weightage on the first one for that reason, right? Could be interpreted that way, but like I said, like I'm also not very clear on why you would want something.
So for example, in the case of like a fraud detection, you would want to weight it for the frauds, right? For the which has less number of samples, I would think.
Right. So I don't think, so are you saying in the fraud scenario, you saw that someone was requesting you to use macro?
No,
Okay,
I'm not
okay.
saying that.
Because I don't think that makes sense. Like those two don't connect
Right.
together.
Right.
Yeah, but to his point, for example, in the Human Protein Atlas, which is discovering the human proteins, which have specific cases, there are 29 classes, and 2 of them are like minuscule in quantity, and they still go for macro averaging.
So that's
a
also
real case.
Right. So my understanding with that is like, for example, if you even look at like the Bengali AI grapheme, where there also it's like
Right.
macro recall, there the intention was like, get me the first grapheme right and don't care about the other two. Like that was the more weightage sort of a thing. That's my understanding.
Yeah. But I mean, in Human Protein Atlas, for example, there wasn't a clear explanation why
I
they
see.
went with that.
Okay.
It seems like macro is the case where you want to penalize any misclassification. In other words, you don't care, like if the class only has a few people in it, you don't say, well, that doesn't count that much. You just say, well, anytime you misclassify something, no matter what class it is, it's equally bad.
That makes sense.
It's equally bad, but at the same time, when you look at the score, that'll look like a higher score. So you'll be thinking that you're doing well. Whereas once you do weighted or micro, you'll actually be taking into account those classes with lesser samples. So then your score is going to fall.
Yeah, the prevalence doesn't matter for macro.
So yeah.
It's kind of like the comparison between the House of Representatives, which is representing populations in each state, versus Senate, which is, there's only one vote per, 2 votes per state, no matter how small the population is.
Yeah, but what Anant was asking was, why would you choose F1 even knowing that you have an imbalanced situation? And to his point, that has been the case. Some explanation that Rakil already provided, but in other cases, it's not that obvious why that metric is chosen, even knowing, because the guideline would be that you would choose micro or weighted if you wanted to factor class imbalance. If your classes are very imbalanced, that's a better way to go to indicate whether you have a classifier that is performing well. But in certain competitions, they do specify using macro. And the reason why is unclear.
So on a general note, can we always say that for imbalanced class, we are always going to use the macro, and for the weighted, and for a balanced class, we are going to use macro? Can we generalize this way?
My personal opinion is that this particular issue is not necessarily as well known as maybe people think. I mean, I think a lot of people are just going ahead and using accuracy and don't really understand if it matters, if the classes are balanced or they don't. Someone put this in there a long time ago and it just kind of stuck. It may not be for any particular reason, or any paper, was addressed a long time ago. I'm not sure that this is like, there's great truth here.
Yeah, I mean, kind of building on what Joseph was saying, my only intuition for why they would choose macro in case of imbalance was I was imagining that in reality, in the field, there might actually not be such a huge imbalance, but it just so happens that in the data set there is imbalance. So you want to watch out for that, and so you're using macro.
Cool. So let's try to finish the last section, multi-output classification. The last type of classification task we're going to discuss here is called multi-output, multi-class classification, or simply multi-output classification. It's simply generalization of multi-label classification where each label can be multi-class. It can have more than 2 possible values. And to illustrate this, let's build a system that removes noise from images. It will take as input a noisy digit image, and it will output a clean digit image. represented as an array of pixel intensity, just like the diminished images. Notice that the classifier's output is multi-label, one label per pixel. So we're talking about like not just one label per image, but like one label per pixel. So we literally have 784 labels per sample, and each label can have multiple values. Pixel intensity ranges from 0 to 255 because each pixel value can range from that. That's an example of multi-output classification system. The line between classification and regression is sometimes blurry, such as in this example, arguably predicting pixel intensity is more akin to regression than to classification. Moreover, multi-output system is not limited to classification tasks. You can even have a system that outputs multiple labels per instance, including both class labels and value labels. Let's start by creating the training and test sets by taking the minutes images and adding noise to their pixel and intensities with NumPy's randint function. The target images will be the original images. So basically, I mean, this was just adding some random noise or random numbers into the original pixel value per array, and using the original images as still as the target images, and kind of train it to see if you can clean the target image. I wonder why he uses KNN here. Any reasons? Any thoughts on this? I don't think he explained.
I think he's just doing it to do something. Canon is usually pretty crappy.
Cool. And I think the code here is, I mean, just fits and predicts that image, and it turns out to claim the image, and we're done. So any questions at this point?
Yes, regarding this last section, that is multi-output classification, I was talking with someone, so he said me that it is another name for this one is a multitask classification. So I tried to look up some use cases for that one. Something I got is that I'm not totally convinced about that one, whether the use case is actually multi-class. So multitask basically. So the use cases is something like that. Say there is a lot of fruits there, and you need to identify first 3 classes, whether there is a mango, there is a guava or pears, or there is something else, let's say. Second thing is that among them, another task is that to identify whether each class is coming under 3 colors, like green, orange itself as a color, and let's say red. So this use case is a correct example of multitask classification, like doing two kinds of classification in the same go. Is that what is this multi-output classification they are talking about?
Anyone has any thoughts? No? Okay.
Anyways, no use. Thanks.
Okay. Well, I guess no one.
Hey, Wenchang, could you go
Sure.
back to the ROC curve section?
Sure.
In the text.
Yeah.
And the paragraph where they talk about when to use PR curve versus ROC curve.
Right here.
Yeah, I actually like. I didn't get much intuition out of this. Like, where was the sentence? Yeah. You should prefer the PR curve when the positive class is rare. how do you explain that? Like, I didn't quite get that. Does anyone understand why that makes sense?
So you're asking why you should use precision
The PR curve,
recall?
right? When the positive class is rare,
Okay, so
or when you care about the, yeah.
I talked about this in my little impromptu lecture on Sunday. Basically, it comes down to class imbalance. And when you have balanced, if you have balanced classes and imbalanced classes, there's no difference with PR, precision recall. Sorry, there's no difference between ROC. ROC is prevalence and variant. So you're always going to get the same ROC curve regardless of whether you have imbalanced classes. Where imbalanced classes are going to start showing up are on something like precision recall curves, which are profoundly affected by them. So it's, you know, his assertion that if you have imbalanced data sets, you have 10 examples of one and, you know, only one example of the other, you should use precision recall. And if you have balanced data sets, you should use ROC. I think that it's, honestly, you should use both, and you should see what's going on, because both spaces map to each other mathematically. And if you have, you're trying to find the best algorithm you can by using ROC and precision recall, you're either looking at the curves or you're looking at the area under the curve, which is a single number. And if you have a, it's mathematically proven that if you have a ROC curve that lies outside of the others, if the ROC AUC is higher, if the precision recall curve lies outside of the others, and the area under the precision recall curve is higher, that's most likely a better algorithm.
Right. So ROC is bad for imbalanced data sets, right? The AUC value.
Not bad, it just doesn't show it up. There's no change, okay?
Okay.
It's
okay.
a feature, not a bug.
Like also it says that if you care about false positives, you should go with PR curve. Whereas false positive is one of the axes in the ROC curve. So even that doesn't make sense to me.
That's part of a larger discussion on information retrieval theory that I missed. Maybe someone else can explain that better, because for me, the two numbers don't mean anything. Other people, they mean more to people in the past than they do to me right now. And this is, I think it's something that was evaluated, and maybe someone has a better handle on it than I do.
Okay,
I mean, just mathematically, like, if you look at precision and recall, let me just go back to the formulas. We have the formulas here. Where's the formula? Under confusion matrix. Right here. So I was thinking, because look at comparing these two formulas, the only difference is the FN, the false positive and false negative. So when you plot these curves, these two curves together, and it's very clear, it would just make it very clear, like when it comes to FP and FN, and perhaps, you know, just mathematical intuition, perhaps that's why he was saying like when you care more about the false positive FP and then the FN, because on that curve, it would just be more clear, because that's the only changing variable of these two statistics.
I think, Stephen, during your talk, you said something about some metric not involving false negatives, or did I remember that wrong?
I think it was about true negatives.
Oh, true negatives. Okay.
Right, and that
Okay.
was that was the metrics that were dealing with segmentation, like F1 and G1 and and F1 and G score, where true negatives essentially go to infinity, so they drop out of the equation. Each different one of the measures and metrics do different things. So I mean, it's for me, again, there's certain stuff I don't know in terms of information theory, and I know that precision and recall come from that, and they were evaluated in the past of science. They were predominantly used in NLP sort of tasks, and again, this is not my spiel. So I think that ultimately you have different tools, and the different tools are useful in different circumstances, and to use a few of them is good. But I can tell you that I've gone through the literature on this stuff a lot, and it's not in any one place. And I think that there are a lot of things that are kind of said wrong and misconceptions that exist regarding this. And because the information is so disparately scattered, there are even multiple terms for the same thing, so that if you search for one thing online, you won't get it because recall, precision, sensitivity, specificity, true positive rate, false negative rate, hit rate, all these things, people refer to them in the academic papers, unless you kind of figure out it's all the same thing. And then one person will have an insight on, like for example, I just put something on cross-validated, regarding AUC, ROC, and accuracy. And Frank Harrell, who's the head of statistics at Vandy, a real smart and nice guy actually, who'll answer you on Twitter. He basically invented something called the C index, which is basically ROC AUC, which is basically informedness. Okay, but to get from C to ROC AUC to informedness is about 3 different papers, where in the first paper they link the 2, the second paper they link the other 2, and then the third paper they link the first and the third. So I mean, it's all in different branches of the literature. So I don't this is just something that was passed down from something he read or something he was taught, and someone who figured this out in information theory. I don't think we should dwell on it.
So I would like to get back to Gautam's question, which I thought was a really good one. In other words, that key point that he made on page 98, I think we should think about it and try to understand it. Wenchang, could you go back to the definitions of precision and recall, those equations that you showed? Yeah, because if you look at the equation for recall, so why might we want to choose precision and recall? Well, the recall is very sensitive to false negatives. If you have if you have a situation where you have very few positives and a lot of negatives, an imbalanced data set, right? Then recall will show when you're getting when you're misclassifying a lot of negatives, and maybe that's not the case for the for the what's that other measure that they use in the Roc curve, the false positive rate.
False positive, right.
So let's look at the equation for false positive rate.
Oh, it's not on the book. If the false
okay.
That's
okay.
true negative by true negative plus false positive.
Negative.
No, it's false
sensitivity.
positive.
That's sensitivity.
No,
so 1 minus sensitivity is what is plotted on the x-axis for
no, that's true positive.
For a ROC curve. 1 minus sensitivity being defined as true negative by true negative plus false positive. You can check the Wikipedia page, but sensitivity is, I'm pretty sure, defined as true negative by true negative plus false positive.
Okay.
Right, yeah. So if that's true, then 1 minus that doesn't involve false negatives, and that so that measure. See, in the precision recall curve versus the Roc curve, the vertical axes are the same, or at least one of the axes are the same, right? The true positive rate is the same as recall, right?
The y-axis is the same.
Yeah, the y-axis is the same. The only difference is the x-axis. And what we've just seen is that the x-axis for the Roc curve doesn't involve false negatives, whereas the x-axis for the precision recall curve does.
Sorry, Joseph. I think ROC is recall versus 1 minus sensitivity, right?
Yes.
1 minus specificity.
Yeah, exactly. Yeah, specificity.
1 minus specificity. Sorry.
Yes.
Right.
Okay.
Yes, and specificity is, I think, Tn by Tn plus Fp.
Yes, when we say sensitivity, it's just the same as recall. Yes.
Yeah. So, but specificity is the x-axis, right? And or 1 minus specificity is the x-axis, and it doesn't involve false negatives, whereas precision is the x-axis for the other curve, and that does involve false negatives. So just by observing that fact, we see that the precision recall curve is sensitive to false negatives, whereas the Roc curve is not.
No, but Joseph, I think to your point, the ROC AOC curve, the ROC curves, what you just said, essentially, because of the way the equations line up, it eliminates, it's only positive and negative, the two are separated, which is the reason that it's prevalence invariant. So whereas the PR curve is sensitive to class imbalance, and it is not, as we saw on Sunday from Stephen's lecture as well, it is sensitive to class imbalance, the PR curve, whereas the ROC curve is not. So you wouldn't, in the case of ROC curve, it's, as Stephen explained multiple times, it's totally invariant to the prevalence, which means it doesn't matter what your FP and FN or how low your true positive case is versus not. It doesn't depend on the quote prevalence of the disease or on how many of your people cheat or anything like that. It's totally class imbalance invariant, whereas that's not the case with PR curves.
Well, let me just kind of try to explain from this. I think intuitively, ROC curve is only trying to basically plot how many positives did you actually identify it correctly, and how many negatives did you identify correctly. And so if you think about that, that doesn't say how many negatives and how many positives you have. It just says whether you've identified correctly in terms of proportion. So that kind of intuitively explains why ROC doesn't explain the class doesn't explain well when it comes to class imbalance, because it's only showing this is like how many this is the false positive rate, right? 1 minus specificity. False positive divided by false positive plus true negatives. That means just like how many of the samples, how many false positives or like the samples that you did not identify correctly. And this is the true positive rates. So when you compare these two, it doesn't say the class imbalance at all, right? It's just proportion.
Yeah, I think that's a good point. I think you've identified that very clearly.
Cool. So I want to kind of just close this. I know we do have some exercises that I originally intend to get to. And Joseph, I want to kind of ask you, or ask anyone, does anyone want to go through this exercise? I mean, not tonight, but like, at another time, perhaps right after Sunday's session, if there are no other sessions planned. Or, people just want to go through it on their own. Up to you guys.
Yeah, that would be good.
Say that again?
Yeah, that would be good to go through the exercises. Yeah.
Cool. And Joseph, do you think we can, is there a session plans right after Sunday's session? Do you think we can perhaps talk about exercises?
Let's see, Sunday we go from 10, right? 10 o'clock to noon or whatever. And there's nothing, we don't have anything planned right after that. But there is, I think there's a reinforcement learning class that meets at noon.
Yeah, I would prefer it if it's not right then, because I would want to attend the RL one.
Yeah.
Okay. How do we decide another time, maybe?
Yeah, or we could pursue it on Slack. People could talk about it on Slack.
Let's perhaps just pin down another time on Slack, and I'll be more than happy to work through this exercise with everyone. So I mean, it is a long exercise because pretty much like 3-4 data sets, right?
Mm-hmm.
But I think it's good to spend time to actually practice what we have learned with those. Some of them are pretty classic Titanic data sets. So I think it's definitely good to kind of go through it, do it yourself, and trial and error, and really, practice. So.
Mm-hmm.